Let us write this expression a little bit more explicitly. Hamiltonian for the helium atom is a function of the two electron labels, variables. But if you remember the expression for Hamiltonian, it contains only space variables. Only space variables. The psi function, the eigenfunction, is written this way, but here, in addition to space variables, there are also spin variables. Space plus spin variables. The fact that Hamiltonian doesn't contain spin variables does not mean that we may forget about spin variables. The spin variables are there. Spin variables enter into the problem by means of Pauli exclusion principle, because Pauli exclusion principle states that psi must change sign when all four, including spin, variables are exchanged for the two electrons. Now, this function for two electrons, psi 1, 2, can be written as a product of a space part times a spin part in the following manner. The notation here is, by space we mean only space variables are contained in the space function. Similarly, in this spin part, which is multiplying the space part, only spin variables. So this function is a function of how many variables? Just two. Because each electron has only one spin variable. There are two electrons. So this is a function of two variables, but these two variables are spin variables. On the other hand, this factor is a function of the space variables of the two electrons. 3 for the first electron, 3 for the second electron. So this is a function of 6 variables, which are the space variables of each electron. And it is this complete function must satisfy the Pauli principle. It must change sign when all four variables are exchanged. The exchange process can be thought of like this. Exchange the space variables, then exchange the spin variables. This way, we are exchanging all four variables of the two electrons. Now, for the this is called antisymmetry requirement. For the antisymmetry requirement to hold, under the exchange, either this function for space exchange or that function for spin exchange must change sign, such that the overall change in the sign must be -1. So there are just two possibilities here. psi space in the exchange. If the space part is symmetric with respect to exchange, then the spin part has to be antisymmetric with respect to spin exchange, so that the overall sign is +1 times -1 will give -1, which is required by the Pauli exclusion principle. The second possibility is the first factor, the space factor, could be antisymmetric with respect to space exchange, but then it must be symmetric with respect to spin exchange, so that overall, when we exchange all 4 variables, the net effect is -1 times +1. Again, it will be -1. So these are the 2 possibilities. Now, because our Hamiltonian does not contain any spin variables, that equation alone does not help us in finding the spin function, but we can obtain the required spin factor by this information here, and also knowing the fact that the full function psi must be eigenfunction of S square and also SC. All of these operators contain only spin variables. So now, determination of psi spin for 2 electrons now, to obtain it, psi spin must be simultaneous eigenfunction of P12 operator, S square operator, and SC. Psi spin must be eigenfunction of P12 operator because of these facts. Psi spin must be eigenfunction of P12 either with -1 eigenvalue or with +1 eigenvalue. Now, to construct the 2 electron spin functions, we have alpha and beta spin functions for a single electron. The first electron has alpha spin or beta spin, and the second electron also may have either alpha spin or beta spin. What about the pair of 2 electrons? Now, taking for the first electron, an alpha spin, and for the second electron, also alpha spin, which I write like this, alpha times alpha. Here, I should write more explicitly this. It is explicitly showing us that this is the alpha function for the first electron, and this is the alpha function for the second electron. Now, in order to simplify the notation a little bit, I'm going to assume that when I write these products from left to right, first electron, then second electron will come. So if I write alpha times beta, I mean number 1, number 2. First electron has alpha spin, second electron has beta spin. On the other hand, if I write beta times alpha, you should understand the first electron has beta spin, second electron has alpha spin. I will never change this order. I will just change the order of alpha and beta in the product. So alpha times taking a spin function for the first electron and taking another function for a spin function for the second electron, we multiply them to construct spin functions for 2 electrons. Possibilities are, because there is just 2 choices for each electron, what is the total number of choices? 2 choices for the second electron, 2 choices for the second electron. What is the total? 2 times 2. There are 4 possibilities for the products. What are they? Alpha times alpha, alpha times beta, beta times alpha times, and beta times beta. These are 4 possible 2 electron spin functions constructed from 1 electron spin functions by multiplication. Now we are saying that these have to be eigenfunctions of all these 3 operators. These are the requirements that we are going to use. Now, the easiest is showing that showing the eigenvalues of z component of total spin angular momentum. Now, I will have to erase this. Later, I will write it again. Now, what is SZ? Sum of spin z component of spin angular momentum for the first electron plus z component of spin angular momentum for the second electron. Remember that S1z contains spin variable for the first electron. It doesn't contain spin variable of any other electron, just 1 electron. Similarly, S2z contains spin variable of the second electron. If we apply this to this product, alpha times alpha, and use the definition, now, there are 2 factors here, alpha times alpha, but which one of these 2 spin functions contain variables of spin variable of only electron 1? The first factor. The second factor doesn't contain it. So this is equal to alpha. Similarly, in this case, here we say it is z component of second electron, but which of these factors contain spin variable of the second electron? The second factor, isn't it? So here, this alpha, the first alpha, because it contains a different type of variable, spin variable of the first electron, it can be factorized. So it is alpha. It will act. Now, what do we know about these alpha and beta functions? S, Z, for for one electron, alpha equals ms times alpha. But what is ms for the alpha function? There are just two possibilities, either plus 1 over 2 or minus 1 over 2. Which one? For the alpha function, alpha spin. And SC for the beta function is minus 1 over 2 times beta. These are ms values. Here, S is a small letter, not a capital letter as I'm writing here, or for the quantum numbers. And M, this M is a small letter. Why? Because of our convention. Whenever we talk about a single electron, we use small letters. All right? But the principle is general. If S is equal to 1 over 2, ms values range from plus s to minus s. If s is 1 over 2, there are just two possibilities, 1 over 2 and minus 1 over 2 for ms. So, this can be replaced with using the, what is the ms quantum number for alpha here? 1 over 2. This is 1 over 2 times alpha. This one is also 1 over 2 times alpha. So what happens? 1 over 2 times alpha plus 1 over 2 times alpha times alpha equals 1 over 2 plus 1 over 2 times alpha, or 1 times alpha. Now, therefore, what do we conclude? Operator alpha times alpha equals eigenvalue alpha times alpha. So, alpha times alpha is an eigenfunction, isn't it? Eigenfunction of which operator? Total z component of total spin angular momentum, because SC means the z component of the total spin angular momentum. Operator function equals number times the same function. This is what we mean by eigenvalue, eigenfunction equation. So alpha times alpha, is it an eigenfunction of this operator? Yes or no? Come on. Yes. What is the operator? SC. What is the eigenvalue? Numerically, what is the value? Plus 1. This eigenvalue is capital MS. Why? Because the operator SC is a function of 2 electron spin variables, not just 1. So we use capital. MS for the alpha times alpha product function is 1. Now, let us see how this is easily generalized. We see that small ms values for each factor, for alpha is 1 over 2, for this one also 1 over 2. Here 1 over 2 for the alpha. For beta, what is it? Minus 1 over 2. Here this is minus 1 over 2. This is plus 1 over 2. Here for both of them has minus 1 over 2 and minus 1 over 2. if you apply this derivation to other products, alpha times beta, beta times alpha, beta times beta, you arrive at the fact that to get the MS, the total MS, you just look up small ms values for each spin function in the product. And then you simply add them. So here, for instance, this 1 over 2 plus 1 over 2. Why? Because both factors have 1 over 2 for the ms, small ms quantum number. In general, we can write it like this. ms for the first factor plus ms for the second electron for 2 electrons. So here if I write, where shall I write ms? Instead of this, let me write ms. For this factor we have found what is the total ms? 1. If we apply it to alpha times beta, we will obtain 1 plus 2 plus this number. And what is the net result? 0. Same thing for this factor, beta times alpha, 0. For this one, we will add up. What do we get? Minus 1/2 plus minus 1/2 minus 1. Now, in general, say we have more than 2 electrons. For instance, alpha times beta times alpha times beta, there is a factor. How many factors do you see here? 2, 4, 5. We are talking about 5 electrons. All right? Now SZ, S1 SZ is S1Z plus S2Z plus S5Z. The Z component of total spin angular momentum for 5 electrons. Such as product of spin functions is an eigenfunction of this SZ. And the eigenvalue for the ms for these 5 electrons, look, this is 1 over 2, this is 1 over 2, this is beta, what is it? Minus 1 over 2, this is 1 over 2, this is minus 1 over 2. It is just a sum of the small ms values. You add up, 1 over 2 cancels this cancels this, the net result is 1 over 2, isn't it? We are just adding small ms values for each electron in the spin product. This is generally true. In other words, for any such spin product, we can write this. Sum ms, add up the ms values in the product up to for all electrons. Here, the example is for 5 electrons. Therefore, spin products are always, they are automatically eigenfunctions of the Z component of spin angular momentum, SC, total SC. At this point, let us examine the same spin products with respect to S square. Our spin functions must be eigenfunctions of S square with eigenvalue S. What are the possibilities for the total spin quantum number for 2 electrons? Remember, the maximum spin quantum S value is number of electrons divided by 2. Here we have just 2 electrons. So what is the maximum? For S, 2 over 2, 1. We had discussed this. And all non-negative numbers smaller than the maximum. So we have just 2 possibilities for the S quantum number. S is either 0 or 1. If S is 0, which word do we use for that case? Remember spin multiplicity. 2 times S plus 1 inwards. If S is 0, 2 times 0 plus 1 is 1. What is the word corresponding to 1? Singlet. If S is 1, on the other hand, what is the spin multiplicity? 2 times 1 plus 1, 3. What is a word for 3? Triplet. Such words, singlet, triplet, are always used to mean spin property. In fact, spin multiplicity. All right? So singlet state, triplet state means spin states. Such words are never used with space part, only with spin part. Okay, now we have just 4 functions, 4 spin products here. Somehow these functions must also be eigenfunctions of S square with eigenvalue. I say eigenvalue S either 0 or 1, but I mean with respect to S square, the eigenvalue actually is S times S plus 1 here. However, we just say, we just indicate the S value. We must have either S equals 0 or S equals 1 in this expression. Look at the highest MS value in the products. What is it? 1. Now, we write MS values are restricted between plus S and minus S. This means that if you take this part, S has to be larger than or equal to MS, isn't it? According to this part. Now, the largest MS value is 1 for these spin products. Therefore, MS or S must be larger than or equal to 1. Next, we ask, is it possible for S, for these products, to be larger than 1? We conclude no by the following reasoning. If S were larger than 1, for example, if S were 2, then there must be MS value with plus 2. But we don't see any plus 2 here. Therefore, we conclude that for these 4 product functions, the largest S value is equal to plus 1. So here, S must be equal to 1 for this function. Here, let us write S value must be 1. Now, if S is 1, then look at here. There must also be MS values, 1, 0, and minus 1. The plus 1 we have already dealt with. From this value, we concluded that S has to be 1, largest S. There must be MS equals 0 and also minus 1. Here we see there are 2 functions with MS equals 0. But there is just one function with ms equals minus 1. Therefore, this function must also belong to ms equals minus 1 of s equals 1. So the s value here for this function must also be 1. So far, that we have done. We need an ms equals 0, 0 component of s equals 1. But remember that there must also be s equals 0. If s is 0, there should be ms equals 0. There are two functions here. One is alpha times beta, the other is beta times alpha. These two functions are different functions. But both of them have ms equals 0, and we are looking for two functions with ms equals 0. One of them must belong to s equals 1, the other must belong to s equals 0. Now, to find them, or to make them more explicit, we now turn into permutation. We know that the spin functions must be either symmetric or antisymmetric with respect to spin exchange. Is this function, let us write P at top. Alpha times alpha. Is it a eigenfunction of permutation operator with exchanges spin only? Look. Here, there are only spin variables here. The permutation operator is exchanging spin variable of the first electron with the second one. Because both functions are alpha functions, after exchange, again, it is alpha times alpha, isn't it? So what is the eigenvalue? 1 plus 1. Similarly, beta times beta. Is it an eigenfunction of the spin exchange operator? Exchange the spin variable of this factor with spin variable of that factor. You get the same thing, isn't it? So this is also symmetric, beta times beta, with respect to spin exchange. So we can write plus 1 here. On the other hand, if you take either this factor or that factor, we obtain, when you exchange the spins, you get beta times alpha. Do you understand the notation? Remember, 1, 2, also 1, 2. From left to right. When you exchange the spin variable of the first electron with the second one, this becomes beta, this becomes alpha. That's what I have written here. Is alpha times beta an eigenfunction of P12? Do we have operator function equals a constant times the same function? Same function is alpha times beta. Remember, beta times alpha is a different function. It doesn't satisfy it. Therefore, alpha times beta is not an eigenfunction of P12. Same thing is the second factor, this. It is also not an eigenfunction of P12 operator. On the other hand, the correct spin functions must be eigenfunctions of P12 for spin exchange. All right? So, what do? We take these two functions. One is alpha times beta, the other is beta times alpha, and form linear combination. So, one is alpha times beta, the other is beta times alpha, multiply this with a constant coefficient, and multiply this with another coefficient, and add. This way, we obtain a spin function. Call this sigma, capital sigma. We want select the coefficients such that this expression becomes an eigenfunction of P12 with P equals +1 or -1, because we know that P12 has just two eigenvalues. One is +1, the other is -1. Remember, if P is +1, we say the function is symmetric under exchange. If it is -1, we say the function is antisymmetric under exchange. For this function to be symmetric under exchange, what must be the relative values of C1 and C2? You can guess it. If you take C1 the same as C2, guess. C1 to be same as C2. Then sigma will be a coefficient times alpha beta plus beta alpha. Is this function, does this function have symmetry property under spin exchange? P12, P12. Now apply this P12 here. You get the first factor becomes beta times alpha. The second factor becomes alpha times beta, isn't it? But the sum, is it same or different from the original expression? Same. So what does it tell us? If we select C1 the same as C2, the sigma function will become an eigenfunction. Operator function equals sigma times which number? Remember, C is part of sigma definition. +1, isn't it? Therefore, such a function, alpha C times alpha beta plus beta alpha, in which C1 is same as C2, is a symmetric function with respect to spin exchange. Similarly, if we select C2 to be minus C1, then we will have, let us call this sigma A. Call this sigma B. It's a constant times alpha beta minus beta alpha. Then this function is also is also an eigenfunction of P12 operator, but this time the eigenvalue is going to be -1. Let us show it. I have taken this expression and now I am expanding it. Now, spin exchange in alpha and beta causes, what is the net result? We had done this before. What was? It was just exchanging spins. What was the first factor is beta, the second factor is alpha. It is alpha times beta, isn't it? So this is beta times alpha minus this is alpha times beta, the net result. Now take the minus sign out. But by definition, what is this? Sigma b. So operator function equals constant times same function. What is the eigenvalue? -1. Okay. Now we can complete our table. We have alpha times alpha. Let us rearrange it this way. Alpha times beta plus beta times alpha times beta. Here you may say a constant. And then we have alpha times beta minus beta times alpha. These are the four functions. This function and that function I have obtained by combining these two. Alpha times alpha and beta times beta are already here. They have the following property. MS value, this is 1, this is 0, this is -1, this is also 0 for MS. P, this is symmetric, this is also symmetric, the third one is symmetric also with respect to spin exchange. On the other hand, this function, we have just shown it, it is antisymmetric with respect to spin exchange. Now, with respect to p value, you see this function is different from the first three. The first three are all symmetric. Now, S quantum number. We know that for the first factor is S is 1. For this factor is S is 1. It is the MS equals -1 of S equals 1. This factor should also belong to S equals 1. This is alpha beta plus beta times alpha. Must be an eigenfunction of S square with S equals +1. How do I infer it? I infer it from the value of P. I see that this function is also symmetric with respect to spin exchange, just like alpha times alpha and beta times beta. So I conclude that S for this factor should be +1. Then here is another MS. Total MS is 0. But remember that I know in this problem there are two total spin values. One is 1, the other is 0. I have found S equals 1 spin functions, and there are 3 such spin functions as there must be. Because if S equals 1, there must be 2 times S plus 1 different spin functions. Here they are these functions. Then I conclude that this function here must be an eigenfunction of S square with S equals 0. All right, these are the spin functions. These are triplet spin functions. Triplet, once again remember, what is the number corresponding to triplet? 3. 1, 2, 3, triplet. 3 different 2 electron spin functions. Singlet means 1, only 1 spin function. The most important difference between the triplet spin functions and the singlet spin function is this p value. Triplet spin functions are symmetric under spin exchange. On the other hand, singlet spin functions are antisymmetric under spin exchange. Now, look at the total. If the spin part is a triplet, that means the spin part is symmetric with respect to spin exchange. Right? So write psi spin triplet. It means one of these spin functions, either that or that or that. It is symmetric with respect to spin exchange. The psi space part must be symmetric or antisymmetric with respect to space exchange, meaning space variables of the 2 electrons are exchanged. Remember, the overall function, when we exchange all 4 space plus spin variables of the 2 electrons, the total function must always change sign, must always be antisymmetric. If this part is symmetric, it is symmetric, then necessarily this part, space part, must be antisymmetric. This is symmetric, must be antisymmetric for the triplet spin functions, for the triplet states. On the other hand, if for psi spin we take the singlet spin function, this function, and multiply it with another space function, because this is antisymmetric with respect to spin exchange, it is necessary that the space part has to be symmetric with respect to electron exchange, so that the overall change is antisymmetric. All right. So the spin parts which we explicitly obtained cause requirements about what kind of expression for psi space to use for triplet states and what kind of psi space to use for singlet states. We will continue next week.